The holographic principle, why black holes rewrite our idea of space. Imagine if everything you see, feel, and experienced, the entire three-dimensional universe, was just a projection from a distant, flat surface. A world where reality itself is a kind of cosmic hologram. This isn't science fiction. It's a serious idea in modern physics. And it all began with a mystery about black holes. In everyday life, the amount of stuff we can put in something depends on how big it is on the inside. A small box holds less than a big box. A planet holds more atoms than a pebble. That's volume. The three-dimensional space inside an object. We've always assumed that the information needed to describe an object also depends on its volume. But in the 1970s, physicist Jacob Bekenstein noticed something strange. Black holes didn't seem to store information based on their volume. Instead, the amount of information, what we call entropy, scaled with the surface area of the black hole's event horizon. The event horizon is the invisible boundary beyond which nothing, not even light, can escape. It's like a point of no return. If you double the surface area of the horizon, the amount of information the black hole can hold also doubles. But doubling its volume, that doesn't matter. Stephen Hawking later discovered that black holes aren't completely black. They emit tiny amounts of radiation, now called Hawking radiation. To make the math work, he had to accept Bekenstein's strange conclusion: a black hole's information content is linked to its surface area. This was shocking because it meant the laws of nature work differently near black holes. Here, the storage capacity of space is defined by a surface, not the volume it encloses. Physicists Gerard T. Hooft and Leonard Susskind took this idea and pushed it further. What if this isn't just a weird black hole thing? What if all of reality follows the same rule? If so, the universe might be like a hologram. The real information about everything we experience could be written on a two-dimensional surface. The three-dimensional world we move through would then be a projection from the data. Think of a credit card hologram. The image you see looks three-dimensional, but all of its information is encoded on the two-dimensional surface of the card. The holographic principle suggests our universe could work the same way. The surface might be unimaginably far away, or even wrapped around the edges of our universe itself. This idea became a central part of string theory. In the late 1990s, Juan Maldacena proposed something called the ADS-CFT correspondence. In this mathematical model, everything happening in a 3D space with gravity can be perfectly described by a 2D surface without gravity. It was the first concrete example showing that the holographic principle wasn't just philosophical, it could be a precise physical theory. If the holographic principle is true, it could be the key to uniting quantum mechanics and general relativity. Gravity, space, and time might not be fundamental at all. They could be emergent properties, arising from quantum information written on a cosmic boundary. Black holes, once thought of as dead ends of physics, are now our best testing grounds for these ideas. By studying their surfaces, their event horizons, we may uncover the fundamental pixels of reality itself. So next time you look at the night sky, remember, everything you see could be stored on a vast, distant surface. A surface that encodes the universe like a cosmic hard drive. And what we call space might just be the ultimate illusion.